Welcome back, everyone. We're diving into graph theory today. A recent paper actually caught my eye on the thresholds of degenerate hypergraphs.
Ah, yes.
By Yu Chen, Jie Han, and Haoran Luo.
Interesting paper, yeah. It really gets to the heart of, well, a fundamental question in graph theory.
Okay.
When do you actually see these structures emerge
Right.
when you're dealing with random graphs?
It's like, where's that line between chaos and order?
Yeah, yeah.
And they start off right on page 1. They use the Erdős Rényi model.
The classic model for generating random graphs. You've got a set of vertices, and for each pair, you basically flip a coin, decide with a certain probability whether you connect them with an edge.
So you're building a graph.
By chance.
Just based on chance.
Yeah.
And the higher the probability, the more connected it gets.
Well.
But what's interesting is, even in all that randomness, there are these patterns.
Exactly, and that's where this idea of thresholds comes in. So the paper's really looking at, as you increase that probability of connection, when do certain structures become likely? Right.
To appear.
And they mention the Kahn and Kalai conjecture, which makes a prediction.
Oh, the Kahn and Kalai conjecture, that's a big one.
Yeah.
It's a major open problem. Really looking at this deep connection between thresholds for these monotone properties in graphs and the influence of variables in Boolean functions.
Right. Yeah, I can see why that would be
yeah, it's a fascinating area.
A big one. And then also on this first page, they bring up this notation of M2G.
M2G. That's a key player here. Essentially, you're measuring the maximum density of edges within any subgraph of G. So you're looking at all the possible subgraphs within G, and you're saying, all right, which one is the most densely packed with edges?
So you're finding the densest part.
You got it.
Okay.
And that density, M2G, that is crucial for figuring out when does G itself become likely to appear in a larger random graph.
So the density of its subgraphs affects the likelihood of G showing up. Okay, so it's all related.
Interconnected, yeah. And then page 2, they get into these degenerate hypergraphs.
Right.
Which is a mouthful.
Yeah, it sounds a little intimidating.
Even for us.
Yeah. But the idea is you've got a hypergraph, and it has specific constraints on its edge density. And there are 2 parameters. These kind of sets an upper limit, like M2G.
Right.
But now it's more broadly applied. How crowded can this hypergraph get?
Even in its densest regions?
Yeah, yeah. And then Anadi adds another layer of control. So even if you look at a subset of vertices, as long as it's not too big compared to the whole thing, the number of edges within that subset can't go beyond a certain limit, and that limit depends on the subset size, and it's like a scaling factor
for that density,
restricting the edge density within these smaller portions of the hypergraph.
Right. So they give some examples.
Yeah, they give 3 examples. They talk about degenerate graphs.
Yeah, which I'm guessing ties back to the M2G.
Absolutely. You're connecting the dots there. So it generalizes that idea. It's saying not only is the densest subgraph limited, but this density constraint applies everywhere.
To the whole graph.
To the whole graph. You got it. And then they talk about planar graphs.
Yeah, so these are graphs that you can draw on a plane.
Right. No edges crossing.
Like a map.
Exactly. Or like a circuit board.
And they can't get too tangled.
Right.
Because of that planar constraint.
And what's cool is all planar graphs fall under this big umbrella of degenerate hypergraphs.
Oh.
It makes sense if you think about it. If you try to cram too many edges into a planar graph,
they're going to cross.
They got to, yeah.
So
planarity itself imposes a limit.
A limit on that density. Yeah, so degeneracy is kind of like this more general idea of sparseness.
A broader notion, yeah.
That includes these planar graphs.
Precisely. And then the third example they give is powers of cycles.
Okay, and I powers of cycles.
Yeah, so imagine you have a cycle, simple closed loop, and you take, say, the square of the cycle. You connect each vertex not just to its neighbors, but also to the vertices 2 steps away.
Oh, okay.
So you can take higher powers, connecting them further and further apart.
And it still stays?
Even though the edges increase, the cyclical structure prevents it from becoming too dense.
Oh, okay. So it's a good example of how edge density can increase, but still be degenerate.
Yeah, exactly. So you see, with these examples, how rich and versatile this concept is.
It seems like they're setting us up for something. Like they're defining the type of graphs.
You're reading their minds.
They're going to look at for the rest of the paper.
You're spot on, and that's what they do. On page 3, they start looking at how likely these degenerate hypergraphs are to show up in bigger random ones.
So like searching for a specific pattern.
In a sea of randomness.
Yeah, a sea of randomness, yeah.
And they introduce a few tools to tackle this. The first one, spreadness.
Okay, spreadness. What is that? How does it help us?
Imagine you're trying to embed one graph, we'll call it G, into a larger graph. Spreadness measures how evenly distributed G's edges are when it's sitting inside H.
So high spreadness means the edges are well distributed.
Yeah, like spread out.
And low spreadness means they're all bunched up.
Clustered together, exactly. And to measure this, they define Q spread.
Okay.
Which basically captures the probability that a random set of Q edges in H actually come from G.
So the higher the Q spread,
the more likely that any random Q edges in H are actually part of G.
Part of that embedded graph.
Okay, how well is G blending in?
Blending in, right.
And then they introduce another concept, vertex spreadness.
Okay, so that's looking at the vertices.
The vertices of G. Yep. How likely are they to land on their corresponding vertices in H?
So how well do they line up
exactly
with their counterparts in H?
You got it. And they give us FAT 2.3, which deals with embedding G into a complete graph.
Complete graph, meaning every vertex is connected to every other vertex.
The most connected you can get.
Most connected graph.
And FAT 2.3 says, if you do that, the distribution of those embeddings has a specific vertex spreadness. It's in vertex spread. E being the number of edges in G, and N being the number of vertices in the complete graph.
So this fact gives us like a baseline for vertex spreadness.
Yeah, a sort of benchmark.
Even in the most connected scenario, there's a limit to how well the vertices of G can align.
Exactly. And this is going to be really important later on.
So they're giving us these tools to analyze how likely these degenerate hypergraphs are.
They're laying the groundwork for a much deeper understanding.
Okay, this is great. I think this is a good place to stop for now.
Okay.
We'll pick up in part 2.
So we're on page 4 now, and this is where they start to connect these spread distributions to the threshold at which G is likely to appear.
Okay, yeah. Like we've built these tools,
right?
Spreadnet, vertex spreadness, and now we're going to see them in action.
Exactly. They start with proposition 2.4, which gives an upper bound on that threshold, basically saying if P, the probability of an edge in H, if it's bigger than a certain value, then G is pretty much guaranteed to be there.
And that value depends on the spreadness properties of G, right?
Precisely. Higher spreadness means a lower threshold needed for G to show up.
So if G is well spread out, easier to find.
Yeah, even if the random graph is pretty sparse. But then they introduce this spiro-spreadness, which is like,
why do we need another type of spreadness?
Well, think of it this way. Regular spreadness looks at the overall distribution of the edges from G inside H.
Okay.
But spiro-spreadness goes deeper. It looks at how those edges are distributed not just globally, but also locally within different size subgraphs of H.
Oh, so it's like zooming in at different levels.
Perfect analogy. And this gives us even better bounds on the threshold.
It's like going from a blurry picture to high definition.
Exactly. And that leads to the heart of the paper. Theorem 2.7.
This seems like a big deal. What does it say?
Theorem 2.7 gives a much improved upper bound on the threshold for degenerate hypergraphs. It says if P, the edge probability in H, is bigger than a certain value, specifically Cn1d, where C is a constant, then G will almost certainly appear as a subgraph of H.
So it tells us exactly when these specific types of graphs, the degenerate hypergraphs, are likely to show up.
Precisely. And the key ingredient here, spiro-spreadness. They analyze the spiro-spreadness of degenerate hypergraphs to get this much tighter bound.
So spiro-spreadness is more than just a theoretical thing. It gives us real results.
Exactly. They even talk about how this connects to robust thresholds, which basically means...
Robust thresholds, what's that?
It's about how stable these thresholds are. Like, what if we change the rules a bit? Instead of a fair coin flip for connecting vertices, we use a slightly biased coin.
So we're messing with the randomness.
Right. Robust thresholds tell us how these little changes affect the emergence of structures. If the thresholds are robust, the structures still appear.
Like a bridge that can withstand some wind.
Exactly. They mentioned some work on Hamilton cycles where this has been studied.
So Theorem 2.7 not only helps us find the thresholds, but also understand how stable they are to these little variations.
Yeah, precisely. All thanks to spiro-spreadness. Pretty impressive, huh?
And then they spend the next 2 pages, pages 5 and 6, proving this theorem.
It's a beautiful proof, really elegant. Are you ready to dig into the details?
Absolutely. Let's break it down.
Okay, so we start with our n-vertex k-uniform hypergraph H. We're looking for copies of G, or degenerate K-uniform hypergraph, with maximum degree.
H is our universe. G is the pattern we're looking for.
Exactly. We want to show that when P, the probability of an edge in H, crosses that threshold, so the CN1D, we're almost guaranteed to find G in there.
All right, so what's the first step?
They define these values for R, called R0, R1, R2, and so on. They represent different scales at which we'll look at the spreadness of subgraphs in H.
So we're zooming in and out.
Exactly. R0, the biggest scale, is DAN, which is the maximum number of edges a subgraph can have and still be degenerate.
We start with the big picture.
Right. Then R1 is INC, where R is related to the sparseness of G.
So we're zooming in a bit, looking at subgraphs with more controlled edge density.
Precisely. And because of the degeneracy, any subgraph of G with at most INC edges must have a certain number of vertices.
Because they need space to spread out.
Exactly. And that number of vertices grows with the number of edges, but with a scaling factor of add.
The add factor prevents them from getting too dense too quickly.
Precisely. It keeps that sparseness in check. For the rest of the Rye values, they use a geometric sequence, each Rye smaller than the previous by a factor of n day.
So progressively smaller subgraphs. Why that specific factor?
It's important for controlling the spreadness at each scale. We need the subgraphs to be small enough to be manageable, but not so small that they're likely to contain G by pure chance.
It's a balancing act.
Exactly, and they chose that factor very carefully. Now, to analyze spreadness at each scale, we use lemmas 3.1 and 3.2, along with proposition 2.4.
Those lemmas, what were they again?
Lemma 3.1 lets us count the possible embeddings of a subgraph from G into H, given some constraints on size and edge density.
So we can count how many ways to fit a piece of G into H.
And Lemma 3.2 counts the subgraphs of G that meet certain conditions.
Like taking inventory of the building blocks of G.
Precisely. Combining these with proposition 2.4, they calculate the probability that a random subgraph of H at each scale actually contains G.
So we're looking at different scales, counting things, and calculating probabilities.
Exactly. And thanks to the degeneracy and those carefully chosen Rye values, this probability stays low.
They've got it all under control.
As we move down through the levels, we get a better and better understanding of how likely G is to appear. Then we reach RL1, the smallest scale. We've shown that the probability stays low even when we zoom into individual vertices and edges.
It's all connected.
Exactly. And now for the grand finale, we use theorem 2.6, Spiro's result.
The final piece of the puzzle.
Precisely. They showed that these Spiro spreadness properties they've established meet the conditions of theorem 2.6.
So theorem 2.6 gives us the guarantee we need. Because of the Spiro spreadness, when P crosses that CN1B threshold, G is almost definitely there in H.
Exactly. A beautiful ending to an intricate proof. We started with a simple question. When do structures appear in random graphs? And we've come so far.
Yeah, and they even have a bonus section on page 7.
Ah, yes. Kelly's semi-sharp thresholds.
Okay, semi-sharp thresholds. What are those?
So remember those thresholds we've been talking about. When P crosses the threshold, the likelihood of finding G jumps up.
Right.
But how sharp is that jump? That's what semi-sharp thresholds look at.
Like how steep that transition is.
Precisely. And Spiro spreadness, our good friend, is important here too. It helps us understand how sharp those thresholds are.
So useful.
They present theorem 4.3. which shows that for certain degenerate hypergraphs, the thresholds get really precise, exhibiting this semi-sharp behavior.
It's amazing how they keep refining our understanding.
And it reminds us that this field is always evolving. Even as we're diving into a recent paper, there are new discoveries being made.
It's exciting to be a part of it.
Absolutely. There's always more to explore in math.
Before we move on, let's acknowledge the researchers mentioned in the acknowledgments.
Yes, collaboration is so important. The exchange of ideas and the pursuit of knowledge together is what makes this happen.
In the last part, we'll look at the bigger picture. What do these mathematical concepts tell us about the real world? So we've gone through all this degenerate hypergraphs, spreadness, Spiro spreadness, even that proof.
Yeah, a lot of detail.
It's been a journey.
It has.
But you might be thinking,
I bet.
What's the point?
Yeah.
Why do we care about all this math?
Well, it's easy to get lost in the symbols and equations.
Yeah.
But this stuff has implications way beyond just pure math.
Okay, so bridge the gap for us. What's the connection to the real world?
Think about networks. They're everywhere.
Oh, yeah.
Social networks, computer networks.
Transportation, even biological networks, like in a cell.
Exactly. Knowing when certain structures pop up in those networks, that's valuable.
Yeah, like knowing the tipping point where a system completely changes.
Precisely. And this knowledge has so many uses. Like in computer science, understanding these graph thresholds, it's essential for designing algorithms.
For routing information, finding communities, optimizing data flow.
All of that. And by understanding these thresholds, we can make those algorithms not just efficient,
right,
but also adaptable to changes in the network.
So it's not just theory.
No.
It affects the technology we use.
Absolutely. And it's bigger than just computer science. Think about epidemiology, how diseases spread.
Oh, right. You can model that as a network, too.
You got it.
People are vertices, and their contacts are edges.
Exactly. Understanding those thresholds, that can help us come up with better strategies to stop a disease.
Things like vaccination campaigns, identifying those who might spread it.
Yeah, even predicting how an outbreak might unfold. It's a powerful tool for public health.
It's like using math to understand disease.
In a way, yeah. And this paper with the degenerate stuff and spirospreadness gives us an even better grasp on these thresholds.
And this knowledge, it's not just about prediction, right? We can use it to design things.
Of course.
Better systems, more resilient, efficient.
If we understand these principles, we can build better communication networks, social platforms, even cities.
It's like using math to build a better world.
Exactly. It shows how abstract math can help us understand and shape the world around us.
As we wrap up, I just got to say the beauty and power of math.
It's amazing.
It's incredible. It seems so abstract sometimes, but it can unlock so much about how things work.
Absolutely. And for you listening, here's a final thought.
Okay.
Could this research help us predict things like trends or how information spreads?
Maybe even how ideas evolve.
It's a question worth thinking about.
It is. Thanks for joining us on this deep dive, everyone. Until next time. Welcome back, everyone. Ready for another deep dive? Today, we're going to wade into the fascinating world of graph theory.
Oh, yeah. Graph theory. It's a rich field, lots to explore.
Absolutely. And this time we have a really interesting paper on degenerate hypergraphs and how they pop up in the Erdős Rényi random graph model.
I mean, if you think about it, we're looking at these special types of graphs.
Yeah.
And then we try to figure out the exact conditions they need to appear in random networks.
Yeah, so it's like trying to find a very particular kind of needle in a haystack.
Exactly.
Except our needle here is this complex mathematical structure.
Right, and the haystack is always changing. It's this network of connections.
Yeah, that's a great analogy.
And figuring out these thresholds, these points where these structures emerge.
Yeah.
That's really important for all sorts of things. Right. Network design, understanding complex systems in general.
Okay, so let's jump right into this paper.
Let's do it.
The abstract kicks things off by giving us some key terms. We have n-vertex K-uniform hypergraph, then degenerate hypergraphs, and of course the Erdős Rényi model.
Yeah, so let's break those down a bit.
Yeah, let's do it.
A hypergraph, you can think of it as a kind of generalization of a graph.
Okay.
Like in a regular graph, you have edges connecting vertices. But in a hypergraph, an edge can actually connect any number of vertices.
Interesting.
So in a K-uniform hypergraph, specifically, each edge connects exactly K vertices.
Okay, so it's like a regular graph.
Yeah.
But those edges can connect like multiple people at once.
That's a good way to think about it.
Interesting. Okay. And then what about these degenerate hypergraphs?
Right. So degenerate hypergraphs, they're special. They have this restriction on how densely connected the subgraphs can be.
Okay.
Basically, they can't be too crowded with edges in any one section.
Got it. So they were like not too dense hypergraphs.
Exactly.
Okay. And we're looking at these inside the Erdős Rényi model.
Yeah, the Erdős Rényi model is a classic way to make random graph. You start with your bunch of vertices and you randomly add edges between them.
Okay.
You set a certain probability for that.
Okay, so we have our random network generator and these not too dense hypergraphs.
Right.
And then the authors introduced this new thing, degenerate hypergraph. What exactly is that?
It's basically refining the idea of degeneracy.
Okay.
This degeneracy condition puts a tighter limit on how many edges can be in a subset of vertices. It takes into account both the size of the subset and the degree of its vertices.
Okay, so it's fine-tuning our definition of not too dense.
Precisely.
Okay, and why is this new definition so important?
Well, the authors point out that this degeneracy It actually captures more types of graphs than the older definitions.
Interesting.
So what they find in this paper could apply to a lot more stuff in graph theory and network analysis.
Oh, that's exciting. Okay, now, the main focus of the paper is to figure out a tighter threshold for when these degenerate hypergraphs appear in the Erdős-Rényi model.
Right.
They use this idea of spreadness to do it. Can you explain what spreadness is and why it helps them find the threshold?
Of course. So spreadness, it's a way to measure how likely a graph is to appear when you're using a random model.
Okay.
Think of it this way. Imagine you're putting together a jigsaw puzzle.
Okay.
And you have one piece you're trying to fit in. Spreadness tells you how many ways and how well that piece can fit.
Okay.
The more spread out the piece is, the easier it is to find a match in the bigger puzzle.
Makes sense.
In this paper, they're looking at how spread out a degenerate hypergraph is within a random graph.
Oh,
the kind you get from the Erdős-Rényi model.
I see. So the more spread out the hypergraph, the more likely it'll show up as you add more connections to the random graph.
That's the idea.
That makes sense. So that's how they find the threshold.
They're looking for that point. Where the hypergraph is spread out enough to almost certainly be in the random graph.
Got it. And then in the paper, they connect vertex spread to spread distributions.
Right. So vertex spread is a way to measure that spreadness.
Okay.
It looks at how likely it is for a set of vertices in your hypergraph to be mapped to a set in the bigger random graph.
Okay.
They have a nice example using a complete K-uniform hypergraph to show this.
Yeah, they show that the uniform distribution of embeddings of a hypergraph G into a complete K-uniform hypergraph is in vertex spread.
Right. It helps to see the concept in action.
Yeah, okay. And then what about these spread distributions?
They come in because they link that vertex spread to the overall chance of finding the whole hypergraph in the random graph.
So by understanding how the vertices are spread out, they figure out how the whole hypergraph is spread out and then how likely it is to appear.
Precisely. And they use a result from Kelly, Miesser, and Pokrovsky to do this.
Okay.
It's proposition 2.4 in the paper. It basically takes a vertex spread distribution on embeddings and turns it into a spread distribution on the copies of the hypergraph.
So they're connecting different levels of spreadness, going from those individual vertices to the whole hypergraph.
Exactly. And that's important because it lets them use some really powerful tools from probability theory to analyze how these hypergraphs show up in random networks.
I see. Okay, now they don't stop there. They go on to introduce an even stronger kind of spreadness.
Yeah.
QR0 arrow O spread. Why do they need that?
Well, the standard Q spread, it only tells you how likely it is for a single edge to be in a random subset of vertices.
Okay.
This new QR0 arrow O spread condition lets them look at different scales of sets. Not just individual edges.
So instead of just one edge, they can see how likely it is for whole groups of edges to be included.
Yes.
That gives them a better picture of how the hypergraph is spreading.
And that's where Spiro's work comes in.
Okay.
Theorem 2.6 in the paper. Based on Spiro's findings, it basically says that if a hypergraph has QR0 Waro spread, then a randomly chosen subset of vertices will probably contain an edge of that hypergraph.
So they're using Spiro's theorem to connect this refined spreadness to the actual probability of finding the hypergraph in a random subset.
Exactly, and that's key to their main result.
Wow, this is really coming together. Okay, so they built this whole framework for spreadness and connected it to finding those hypergraphs in random networks.
Yeah.
What's next?
Now they can prove their main theorem.
Okay.
The one that gives a tighter upper bound for the threshold of degenerate hypergraphs.
Okay, I'm ready to dive into that proof.
Yeah.
But I think we should pause here for now.
Yeah.
And pick up the details of the proof in part 2.
Sounds good. This is a complex proof. Lots of intricate steps.
Yeah.
Best to take it one piece at a time.
All right, so we're back and ready to tackle that proof for the main theorem.
Yeah, this is where it gets really interesting. They start by setting up the two main cases they need to prove.
Okay, right. Their goal is to show that their spread distribution fits this stronger QR0L spread condition for all the possible values of T, which is the number of edges in a subset of vertices.
Yeah, and if they can prove that, then they can use Spiro's theorem to directly connect their spread distribution to the chance of finding the whole hypergraph in a random subset.
Okay, so what are the two cases they look at?
The first case is for larger values of T.
Okay.
The second one handles smaller values.
So they're breaking it down based on the size of the subgraph they're looking at.
Exactly.
Okay, so for the first case with those larger T values, what's their strategy?
They use the fact that the graph is degenerate.
Okay.
And they already have a spread distribution from proposition 2.4.
Right. We talked about that in part 1.
So how does degeneracy help them here?
Yeah, what's the connection?
Well, it guarantees a certain level of sparsity in the hypergraph.
Okay.
So they can set a limit on the probability of finding at least T edges from a subset as within a random copy of the hypergraph.
So because the graph isn't too densely connected, they can limit how likely it is to find a bunch of edges in a specific subset.
And their argument shows that this limit actually satisfies the QR00 spread condition for those larger T values.
That's pretty clever. They're using the structure of the degenerate hypergraph to their advantage.
Exactly.
Okay, but what about that second case where T is smaller?
Yeah.
It seems like finding a small number of edges might be harder to control.
It is a bit trickier, but they use 2 lemmas, lemma 3.1 and lemma 3.2. One's about counting embeddings, the other's about counting subgraphs.
So instead of bounding probabilities, they're counting how many ways their target graph could fit into the bigger hypergraph.
Exactly, and they're very careful with their counting because of those restrictions from the degeneracy condition.
That sounds pretty complex.
It is, but we can break it down.
Yeah, please do.
They start by looking at the number of components, which they call C.
Okay.
In the subgraph made by the edges in S.
Remind me what a component is again?
It's a connected piece of a graph where you can get from any vertex to any other vertex by following edges.
Okay, so they're grouping the subgraphs by how many separate connected pieces they have.
Right, and why that's important is it lets them use different counting arguments depending on the structure of that subgraph.
Okay, so they split it up based on the number of components, then what?
They use a really neat combinatorial argument to bound the number of possible subgraphs with C components.
So they've found a way to control how many subgraphs they have to consider.
Exactly, and that's a key part of the proof.
Okay, so then what do they do with that information?
They combine it with that spread distribution they got earlier. This lets them show that the probability of finding at least T edges also satisfies the QR0 spread condition, even for the smaller T values.
So they've connected those two cases.
Yes.
Showing that their spread distribution has this spreadness property, whether T is big or small.
Exactly. And that's crucial because now they can finally use Spiro's theorem.
Right. Spiro's theorem links spreadness to the probability of finding an edge in a random subset.
Yeah.
So how does their final argument work?
They put together their proven QR0 arrow spread property with Spiro's theorem, and they conclude that if the probability P of choosing an edge is greater than or equal to a certain constant divided by N1D, then the probability of finding their hypergraph in the random graph is very high.
That's it. That's their main result.
Yes.
They found a new, tighter upper bound for the threshold.
They have, and the way they did it, by carefully building this concept of spreadness and connecting it to these existing results in probability theory.
Yeah.
It's really elegant.
I agree. They took this abstract idea and used it to prove a concrete result about how these hypergraphs show up in random networks.
It's a great example of how theoretical math can help us understand complex systems.
Absolutely. Okay, so we've gone through their mathematical argument now.
We have.
In part 3. Let's step back a bit and talk about what their findings mean more broadly.
Sounds good.
What does this tighter threshold mean for network analysis and other fields?
Yeah.
What new research could come from it? Stay tuned for the exciting conclusion of our deep dive. All right, we're back for the final part of our deep dive. We've really broken down those degenerate hypergraphs and their thresholds.
We have.
Now let's step back a bit and look at the bigger picture.
Yeah, time for the so what.
Exactly.
Yeah.
We've been into those mathematical details.
Deep in the weeds.
Which is cool, but these findings could have implications in all sorts of fields.
Oh.
One thing that caught my eye was the authors mentioning robust thresholds towards the end of the paper.
Yeah.
It seems like that could be really useful for understanding real-world networks, especially when we're talking about resilience.
Absolutely. Remember, a threshold tells us when something reliably appears.
Yeah.
A robust threshold goes further.
Okay.
It means that the appearance is not only reliable, but also resistant to change.
Oh, interesting.
Like, even if things get shaken up a bit, the structure is likely to still be there.
So imagine applying that to something like a communications network.
Yeah.
If engineers knew those robust thresholds for certain structures,
right,
they could design networks that are tougher and can handle disruptions better.
Exactly. Think about a network built to resist damage or attacks. By understanding those thresholds for the important parts, you can make sure the network stays working even if some parts get taken out.
That's a powerful idea.
It is.
And it's not just about resilience. The authors also mention how their work can help figure out the thresholds for specific graph structures, like the art power of Hamilton cycles.
Right.
What makes those structures so interesting?
Well, Hamilton cycles are these paths in a graph.
Okay.
They visit every vertex exactly once before going back to the start.
Okay.
The art power of a Hamilton cycle connects vertices that are steps away from each other along that cycle.
So it's like expanding the connections based on how close they are along this special path.
That's a good way to put it.
And why are those structures so important?
They show up in all kinds of areas.
Okay, like what?
Transportation networks, scheduling problems, even DNA sequencing.
Wow. That's a wide range.
Yeah.
So if we understand the thresholds for these structures, we could improve those systems, make them more efficient and robust.
You got to imagine optimizing delivery routes for logistics or scheduling tasks in manufacturing. Knowing when these Arth power Hamilton cycles pop up could lead to some big improvements.
This is really amazing. We started with this abstract idea of spreadness.
Yeah.
And now we're talking about making tougher communication networks and optimizing complex systems.
It just shows how theoretical math can have real-world impact.
Absolutely. And that's what makes this field so exciting.
It really is that pursuit of abstract knowledge can lead to breakthroughs in practical applications.
I couldn't agree more. This deep dive has been a fantastic journey.
It has.
As we wrap up, what are some key things you want our listeners to think about?
I'd say never underestimate abstract thinking.
Yeah.
Sometimes the most profound insights come from exploring ideas that seem far removed from our everyday lives.
I totally agree. And building on that, embrace curiosity.
Oh, that's important.
Don't be afraid to ask questions, explore things you don't know, and connect the dots in new ways.
You never know what you'll find.
Exactly. And lastly, I want to remind everyone that knowledge is a team effort.
Right.
This paper builds on the work of so many mathematicians who came before.
We're all standing on the shoulders of giants.
That's a great way to put it. A huge thank you to all our listeners for joining us on this deep dive into the world of degenerate hypergraphs.
Thanks, everyone.
We hope you've learned some cool things and gained a new appreciation for the power of mathematics. Until next time, keep exploring, keep learning, and keep pushing the boundaries of knowledge of knowledge. All right, let's jump right into it today. We're doing a deep dive on this paper. On the thresholds of degenerate hypergraphs. I've been really looking forward to this one. Graph theory, always a good time.
Oh, yeah. Always interesting to peek under the hood and see how networks really work, you know? And this paper, this is a fascinating one, really looking at how these structures, these graph structures, when do they sort of pop up? Like, what's the tipping point?
Yeah, the tipping point. I like that. So we have this paper, and okay, it's a bit dense, got to be honest, but it seems like the core, the heart of it, it's all about figuring out those tipping points.
Yeah.
Right? And they're doing that for they call them degenerate hypergraphs. What exactly are those?
Degenerate hypergraphs, right? So basically, it's a type of hypergraph where every single subgraph, no matter how you slice it, every subgraph has at least one vertex with a degree of, at most, D.
Degree of D. Okay, so if D is 2, let's say, that means every subgraph has at least one vertex, and that vertex is connected to, at most, 2 other vertices.
Exactly, you got it.
Okay, so the paper, I noticed they throw in all these examples, K3, planar graphs, even powers of cycles. Are these just examples of what these degenerate hypergraphs can look like?
That's exactly it. They're grounding this idea of degeneracy, this whole concept, with some familiar, friendly faces, you could say. So K3, the simple triangle, that's your classic 2 degenerate graph.
Right, okay.
And then you have planar graphs. Think of those like maps where no 2 bordering regions have the same color. Those are degenerate too.
Okay, yeah, I can see that.
And then powers of cycles, well, those help us see how connections in a graph, in a circular graph specifically, how those connections can be, manipulated, I guess you could say, to create different levels of degeneracy.
Different levels, okay. But the paper, it doesn't just stop there, right? It goes beyond just these examples. They talk about the degenerate hypergraphs. What's with the A? What's that all about?
Yes, the R. That little symbol is actually, it's kind of a big deal. It introduces like this this finer level of control over the degeneracy. It helps us define how sparse the connections are within the whole hypergraph.
So it's not just about having vertices with, a limited number of connections.
Right, exactly. It's not just about the number. It's also about how those connections are spread out, how they're distributed.
Okay, so it's like it's adding a layer of complexity. It's not just the quantity of connections, but the arrangement.
Exactly.
I see. So it seems like they're really trying to push our understanding further with this paper. And I noticed they compare their work a lot to previous research. What are some of the big advancements that they're claiming to make here?
Well, I think one of the real standouts is theorem 1.4. It's a new upper bound for the threshold of these degenerate hypergraphs.
An upper bound, okay.
In simpler terms, they found a tighter limit, a tighter constraint on the probability at which these structures, these hypergraphs, are likely to just sort of pop up in, like a random collection of points and connections.
Okay, so walk me through this theorem 1.4 then. They have this inequality. They write THG and D. What are all the pieces here?
Sure. So it D, that represents the threshold function for a specific graph, a graph G. And N is the number of vertices in that graph, right? And D, well, we already talked about D, that relates to the degeneracy of the hypergraph. So this inequality, what it's saying is the probability, the chance that a graph G will appear, it's bounded by this expression, this formula, with the number of vertices and the level of degeneracy.
So does that mean practically that we can now predict better, more accurately when these complex structures might appear, let's say, I don't know, in a real world network?
Absolutely. That's one of the key takeaways here. For example, think about the formation of communities in a social network. This theorem, it could give you a much better grasp of the conditions, the specific conditions under which those communities, those little groups, are likely to emerge.
That's pretty cool. Now, I know they also connect this theorem to the Conjecture conjecture, which I vaguely remember. It has something to do with predicting graph emergence. Can you remind me about that one?
Oh, of course. So the Conjecture conjecture, it basically proposes this connection, this link between the expected number of copies of a graph and its threshold of appearance. So what it suggests is if you expect to find, a bunch of copies of a specific graph within a random graph, well, then that graph is very likely to show up, to appear as you increase the density of the connections in that random graph.
Okay, that makes sense.
And this theorem 1.4 that we're talking about, it really adds to this whole line of inquiry. It improves our grasp of these thresholds, but specifically for this particular class of graphs, this particular type of graph.
So they're refining our tools for predicting how networks evolve and what kind of structures they're likely to form. And that has implications for all sorts of things, right? Social science, computer science, all that.
Oh, absolutely. It's far-reaching. And they build on these ideas. They keep going. And they look at a specific type of graph. They call them locally sparse regular graphs in Corollary 1.5.
Okay, I have to admit that one threw me off a little. Can we break it down? What makes those graphs so interesting, and what is the equation that they provide for them? What does it tell us?
Yeah. So locally sparse regular graphs, these are interesting because they have a very specific structure. Each vertex, each point, it has the same number of connections, the same degree. That's the regular part. But if you zoom in, if you look at just a small neighborhood around any vertex, the connections are actually pretty sparse, relatively speaking. And the equation they give, it's like a precise condition to check if a graph, is one of these, if it falls into this category. It relates the number of connections that are crossing the boundary of a small set of vertices to the size of that subset.
Okay, so why would we care about the threshold for these specific graphs? What's the practical use of knowing that?
Think about it this way. A lot of real-world networks, they need to be robust. You want the network to keep working, even if some connections fail. And these locally sparse regular graphs, they can be vulnerable because the connections within those small neighborhoods, those small areas, they're limited. So those areas can become bottlenecks if they get disrupted, if some connections fail.
So knowing the threshold, knowing when they're likely to pop up, could help us design networks that are more resilient, like by understanding where those weak points might form.
Exactly. Like imagine a communication network. You could use this knowledge to avoid to avoid designs that are likely to develop those vulnerable structures, to make sure your network is strong and reliable.
Okay, that's a great example. Now they go on to actually they build a specific type of this locally sparse regular graph. Should we go through all the details of that construction?
Well, I think it's worth touching on the key features at least. So they start with these disjoint cliques. Basically, these are complete graphs where every single vertex is connected to every other vertex. But these cliques, they're separate, they're disjoint.
Right, so little islands of complete connection, but no connections between the islands.
Right, and then they start adding connections carefully, strategically between these cliques to build a bigger regular graph. But they do it in a way that keeps it locally sparse, keeps that property.
And they keep talking about edge boundaries. How does that fit into the construction?
So the edge boundary, remember, it's all the connections that are crossing between a subset of vertices and the rest of the graph. And in their construction, they're very clever about how they arrange those connections. They do it so that the edge boundary for certain subsets, it's minimized. And this helps them understand the lower bound, like the minimum possible value for edge boundaries in these types of graphs.
Okay, so they're using this very specific construction to learn more about the properties of these locally sparse regular graphs, especially about how vulnerable they might be based on their edge boundaries. And this leads us to the remarks section. They have some pretty interesting observations in there about the implications of their results, the bigger picture.
Yeah, that section's full of gems.
One thing that caught my eye was their statement that the upper bound, that it's optimal, the best possible in some cases. What's the significance of that?
So that means for those specific scenarios, they found the best possible upper bound. It makes their findings even stronger because it shows that their result is as tight as it can be. It solidifies the mathematical power, no wiggle room.
Got it. And they also talk about the ratio, THGPEG. And they're very happy about eliminating a logarithmic factor. Can you remind me what that ratio even means and why is getting rid of that factor such a big deal?
Right. So that ratio, it connects the threshold of a graph, when it's likely to appear, to the expected number of copies of that graph in a random graph. And by getting rid of that logarithmic factor, they're improving our understanding of this relationship, this connection between those two things. And it could potentially even move us closer to proving the Concolli conjecture, which we talked about earlier. That's all about predicting graph emergence.
Okay, yeah. So they're making some real progress in refining those predictive tools. They're not just saying, hey, this structure will emerge. They're getting closer to saying it'll emerge with this specific probability within this range.
Precisely.
So it seems like they're making great strides, really. But I also noticed they're very upfront about the limitations of their work. Yeah. Specifically about that condition, that IDGO. Why is that constraint there?
Good catch. So that condition, it's essential because it excludes certain types of graphs that behave differently. They don't fit within the framework of the results, things like Hamilton cycles or spanning trees.
And those are.
So a Hamilton cycle, just to give you an example, it's a path that visits every single vertex in a graph exactly once. And to create one of those, you need a certain level of connectivity that's not captured by a degenerate condition, not when I is 0.
Okay, so it's like their results, they're powerful, but they have boundaries, they have limits.
Yeah.
Right now, the paper shifts gears at this point, and it goes into this whole concept of spreadness. I'm curious, what's that all about? What is spreadness, and how does it relate to understanding these graph thresholds?
Yeah, so spreadness, it's basically a way to measure how evenly the embeddings of a graph are distributed within a larger structure. Imagine you have a small graph, right, and you want to place it inside a bigger graph. Spreadness tells us how likely it is that different parts of that small graph will end up in different parts of the larger one.
So it's like how spread out those embeddings are. Okay, so they have these definitions for spread and vertex spread. Can you unpack those a little bit?
Let's try to visualize it.
Yeah.
Imagine scattering seeds on a field. Spread, as defined in definition 2.1, would look at the overall distribution of those seeds across the entire field. Are they clumped together? Are they evenly spread?
Okay.
And vertex spread, that's definition 2.2. It zooms in, it looks at individual points on the field. How likely is a seed to land on any specific point?
Okay, so it's like for spread, we're looking at the whole field. And for vertex spread, we're looking at like individual spots on the field.
Exactly.
And they use a complete graph as an example for vertex spread. In fact, 2.3, can you walk me through that?
Right. So in a complete graph, every single pair of vertices, every pair of points, they're connected. So if you're randomly embedding a smaller graph into this complete graph, each vertex of the smaller graph has an equal chance of landing on any vertex of the bigger one.
Okay, so it's like perfectly spread out.
It's a uniform distribution.
Yeah.
And that demonstrates a certain level of vertex spread, which they quantify in that fact 2.3.
So it's like saying in a perfectly connected network, information or connections, they're equally likely to spread to any point.
That's a great way to put it.
Now, they introduced this Spiro's stronger notion of spreadness in definition 2.5. What's so special about Spiro's take on this whole spreadness thing?
So Spiro's definition, it adds a bit of a twist. It's more complex. It considers not only the spread across the individual vertices, but also the spread across sets of vertices, sets of different sizes. So it's like looking at, going back to our field analogy, it's like looking at how those seeds are spread out, not just individually, but also in clumps, in groups of different sizes.
Oh, so instead of just looking at single points, Spiro's looking at like clusters of points and how those clusters are distributed.
You got it. And it turns out this refined definition is super important for proving their main result in theorem 2.7.
And I see there's this connection to semi-sharp thresholds, which seems to lead into theorem 4.3. Can you talk about that connection a little?
Right. So semi-sharp thresholds, they basically mean that the probability of a graph appearing, it increases very rapidly within a specific range of probabilities. And Spiro's spreadness, it helps us establish that those semi-sharp thresholds exist. And that lays the foundation for theorem 4.3, which really dives into this whole phenomenon.
Okay, I see. So we're starting to see how all these pieces fit together. I think this might be a good place to pause and pick up next time before we jump into the actual proof of theorem 2.7.
Yeah, that sounds like a good plan. We've covered a lot of ground, and that proof, it's a bit of a beast.
All right, so we'll dive into the heart of the math next time. Until then, keep those graph theory brains buzzing, everyone. Welcome back. We're in the thick of it now with on the thresholds of degenerate hypergraphs. Yeah. Last time, we laid the groundwork, right? We talked about degenerate hypergraphs themselves, these interesting thresholds, and then of course the whole concept of spreadness. And now it gets real. We're diving into the proof of theorem 2.7.
This is where the magic happens. It's a beautiful proof. Really showcases the power of combinatorial arguments, probabilistic reasoning, all that good stuff. It's the authors really dissect this problem piece by piece, and then they weave it all together into this elegant mathematical tapestry.
Okay, I'm excited, but I got to be honest, a little intimidated too. Can you maybe give us a roadmap before we get lost in the mathematical jungle here? What are the big milestones, the key steps they're trying to hit in this proof?
Of course. So the ultimate goal here is to prove that the probability distribution, which we touched on last time, it has Spiro spreadness, but with a constant L. Remember, Spiro spreadness, it's not just about how individual vertices are spread out. It's about how sets of vertices, sets of different sizes, are spread out within a larger graph.
Right. Like those seeds scattered on the field. We're looking at individual seeds, but also at clumps of seeds, different sizes.
Exactly. And proving this property about all, it's a big step toward understanding those graph thresholds, those tipping points we keep talking about.
Okay, so how do they get there? They start with lemmas 3.1 and 3.2. What are those all about? What role do they play?
Those lemmas are essential. They're all about counting and bounding certain quantities related to hypergraphs. Lemma 3.1, that one focuses on bounding the number of possible embeddings of a hypergraph, let's call it H, into another hypergraph G.
Okay, so like how many ways can we fit one graph inside another graph?
Exactly, like fitting a puzzle piece into a bigger puzzle. How many different ways can you do it?
Got it. And what about lemma 3.2?
Lemma 3.2, that one deals with counting the number of subgraphs, but within a specific hypergraph that meets certain criteria. Like they might have a specific number of edges, or no isolated vertices, a particular number of connected components, that sort of thing. It's like categorizing and tallying up different types of structures within a larger network.
So lemma 3.1 helps us limit the possibilities, and then lemma 3.2 helps us sort of categorize what's within those possibilities.
That's a good way to think about it.
Okay, so armed with those tools, how did they proceed to prove that it has spiro spreadness?
Well, they're very clever about it. They divide the problem into cases based on the value of a parameter t.
Okay, t, and what's is representing here?
It represents the size of the intersection between a set of edges and a potential subgraph. So they're breaking the problem down into smaller chunks, more manageable chunks, each focused on a different size of that intersection.
Right. Okay. So each case is like, okay, what if the intersection is this big? What if it's this big?
Precisely. And for each of those cases, they carefully apply those lemmas we talked about, lemmas 3.1 and 3.2, and they use properties that are specific to degenerate hypergraphs to come up with to derive bounds on certain probabilities. It's a very intricate dance between combinatorial arguments, counting things, arranging things, and probabilistic reasoning, figuring out the likelihood of certain events.
It sounds pretty complicated.
Oh, it is. It is. There are a lot of twists and turns in the math. Clever manipulations, inequalities, all that. But every step, it serves a purpose. It's all very carefully orchestrated to lead us to the conclusion, to the result thereafter. It's really quite impressive.
And I imagine they have to be very careful about that A0 condition through this whole process, right? Because that's defining the boundaries of their work.
Absolutely. That condition is it's like a safety net. It makes sure that all their conclusions, everything they're saying, it applies specifically to the type of hypergraphs they're studying, staying within those boundaries.
Right, right. So after all that, after tackling all those cases, they finally show that ERL actually does has spiro spreadness. That must feel like a victory lap, right? A big moment.
It is a big moment, and this is where that claim they made about eliminating the logarithmic factor, this is where that comes into play.
Right, right. They were pretty proud of that. Can you remind me why that's such a big accomplishment?
Of course. So they've established the spiro spreadness of aura, right? And now they can use that property to refine the bounds on the Seychel function. And it's during this refinement process that they very skillfully remove that logarithmic factor, and that results in a tighter bound, a more accurate bound for the threshold.
So it's like they're sharpening their predictive tools even further. They're not just saying, hey, this structure might appear. They're getting closer to saying it will appear, and it will appear with this specific probability under these conditions.
Exactly. And that level of precision, it's incredibly valuable for understanding how networks behave, how they evolve over time, all that.
Okay, now before we move on to the last part of our deep dive here, there's that additional notes section, and they bring in Tom Kelly. He's got an even stronger notion of spreadness, it seems. What's Kelly bringing to the table? What's his contribution?
Kelly's work is it's fascinating. It's like adding a turbocharger to an already powerful engine. He introduces an even more refined way of measuring spreadness. He builds on Spiro's work, but he takes it even further, gives us an even more nuanced understanding of how these graph embeddings are distributed. Remember how we talked about Spiro's spreadness, considering the spread of individual vertices and sets of vertices?
Right. Like looking at those seeds and clumps of seeds on a field.
Exactly. Well, Kelly takes it a step further. He's not just looking at individual seeds and clumps. He's looking at the patterns within those clumps, how those patterns themselves are spread out.
Wow. Okay. So it's like zooming in even further, adding another layer of magnification.
Yes, exactly. And this refined notion of spreadness, it allows us to achieve even more precise result about graph thresholds. It leads to theorem 4.2, which gives us an even sharper bound on the probability of finding a specific subgraph within a random graph.
So we're getting better and better at predicting when these structures are going to show up, more and more accurate.
That's the goal.
Okay, and then there's the grand finale, theorem 4.3. What's so special about this theorem, and how does it tie everything together?
Theorem 4.3, it's the culmination of all the work that came before it. It really shows the power of Kelly's refined spreadness. They show that by using this new tool, this new way of looking at things, we can significantly improve the error probability in our predictions about graph thresholds. In simpler terms, we can be even more confident in our assessments of when and how certain graph structures are likely to emerge.
So not just predicting if they'll emerge, but how accurate our prediction is.
Precisely.
And I remember them mentioning a pretty exciting conclusion about sharp thresholds. What's that all about?
Yes. So they conclude that nearly maximally the degenerate hypergraphs, these particular types of hypergraphs that are almost as dense as possible within the degenerate category, they exhibit sharp thresholds.
Okay, and what does that mean exactly? Sharp thresholds.
It means that for these hypergraphs, the probability of them appearing, it jumps dramatically within a very narrow range of conditions.
Oh, so it's like a sudden phase transition. It goes from almost certainly not there to almost certainly there very, very quickly.
Exactly. And this sharp threshold phenomenon, it's incredibly important for understanding how networks evolve, how these sudden shifts in behavior can happen. It's like it gives us a mathematical framework for explaining those tipping points, those moments when a network suddenly abruptly transitions from one state to another.
Wow, that's pretty amazing. It's fascinating to think that these abstract mathematical concepts can give us such profound insights into how real world systems work.
It really highlights the beauty and power of mathematical thinking, doesn't it? By exploring these abstract ideas, we can gain a deeper understanding of the world around us. We can uncover hidden patterns. We can reveal the mechanisms that drive these complex systems.
Okay, well, this whole deep dive has been incredible. We started with the basics of degenerate hypergraphs, then we went into this world of spreadness, and now we're here with theorem 4.3. Quite a journey.
It has been, and it's a testament to the endless possibilities of mathematical exploration, the power of human curiosity.
Right. So to our listeners, we encourage you to keep exploring, keep asking questions, keep pushing the boundaries of your own understanding. The world of mathematics is it's full of wonders just waiting to be discovered.
Who knows what groundbreaking insights you might uncover.
And until next time, keep diving deep into the fascinating world of knowledge. Welcome back to our deep dive on the thresholds of degenerate hypergraphs. We've been through a lot together, haven't we? Degenerate hypergraphs, spreadness, that pretty intense proof of theorem 2.7, and now we're in the home stretch. We're going to talk about Tom Kelly's work in that really interesting theorem 4.3.
Yeah, Kelly's work it's really something. He takes this whole idea of spreadness and pushes it even further, creates an even more powerful tool to analyze, how these graph embeddings are distributed. Remember how we were talking about Spiro's spreadness, looking at both individual vertices and sets of vertices?
Yeah, like those seeds scattered on a field, right? Individual seeds and clumps of seeds, different sizes.
Exactly. Well, Kelly, he goes a step further. He's not just looking at individual seeds and clumps. He's analyzing the patterns within those clumps, how those patterns themselves are spread out.
Okay, so it's like adding another layer of magnification to our analysis. We're not just looking at the distribution of the elements, but the distribution of the distributions.
That's a great way to put it. It's really powerful, and this refined notion of spreadness, it lets us get even more precise results about those graph thresholds. It leads to theorem 4.2, which gives us an even sharper bound on the probability of finding a specific subgraph, within a random graph.
So we're just getting better and better at predicting when these structures are going to pop up, more and more accurate.
That's right.
Okay, and then there's the big finale, theorem 4.3. What makes this theorem so special? How does it tie everything together?
Theorem 4.3, it's like the culmination of all the work that came before it. It really showcases the power of Kelly's refined spreadness. They show that by using this new tool, this new way of looking at things, we can really improve the error probability in our predictions about those graph thresholds. So basically, we can be even more confident, even more certain in our assessments of when and how these structures are gonna emerge.
So it's not just predicting if they'll emerge, but how accurate our prediction is. We're getting more certain about our certainty.
Exactly.
And I remember them mentioning a really interesting conclusion about about sharp thresholds. What was that all about?
Yes. So they conclude that nearly maximally degenerate hypergraphs, these specific types of hypergraphs that are almost as dense as possible, within that degenerate category, they exhibit these sharp thresholds.
Sharp thresholds. But what does that actually mean?
It means that for these hypergraphs, the probability of them appearing, it jumps, it increases dramatically, but within a very, very small range of conditions. Like a tiny change can make a huge difference.
So it's like a phase transition almost. It goes from almost certainly not there to almost certainly there, but very, very quickly, like a switch flips.
Exactly. And this sharp threshold phenomenon, it's crucial for understanding how networks, how they evolve, how these sudden changes in behavior can happen. It's like it gives us this mathematical framework for explaining those tipping points, those moments when a network suddenly abruptly shifts from one state to another.
Wow, that's pretty incredible. To think that these abstract mathematical concepts can give us such profound insights into how real systems work.
Yeah, it really highlights the beauty and the power of mathematical thinking, doesn't it? By exploring these abstract ideas, we can gain a deeper understanding of the world around us. We can uncover these hidden patterns. We can see the mechanisms that drive these complex systems.
Well, this whole deep dive has been amazing. We started with degenerate hypergraphs, and we went into this whole world of spreadness, and now we're here. We're talking about theorem 4.3. It's been quite a journey.
It has been a fascinating journey, a testament to the endless possibilities of mathematical exploration, to the power of human curiosity.
Well said. And to our listeners, we encourage you to keep exploring, keep asking those questions, keep pushing the boundaries of your understanding. The world of mathematics, it's full of wonders just waiting to be discovered. Who knows what groundbreaking insights you might uncover. Until next time, keep diving deep into the fascinating world of knowledge. Hey everyone, welcome back. We're diving into some really cool math research today on the thresholds of degenerate hypergraphs.
Yeah, fascinating stuff.
You gave us this paper on the thresholds of degenerate hypergraphs.
By Jie Han and Luo, right?
Yes, by Yu Chen, Jie Han, and Haoran Luo. And I'm excited to break this down because this is like a problem that's been kind of bugging mathematicians for a while.
It has, and this paper is a really big step forward, I think.
Yeah, I think so too. And I know you've been following this area pretty closely, so
yeah, keeping an eye on it.
Awesome. Well, let's just jump right into it.
Sounds good.
The abstract kind of throws us right in with this idea of degenerate hypergraphs.
Yeah, it jumps right in.
Can you remind us what those are and what these authors are trying to figure out about them?
Sure. So to understand degenerate hypergraphs, it helps to think about what a hypergraph is in the first place.
Okay.
It's basically like a regular graph.
Okay.
But instead of edges just connecting two vertices, an edge can connect any number of vertices.
Oh, okay. So a little more general.
Yeah, more general, exactly. And then when we say it's k-uniform, that means every edge connects exactly k vertices.
Okay, so that's where that k comes in.
Exactly. And then the degenerate part adds this whole other condition about how the edges are spread out, like it can't be too densely connected. Right. The d and the error kind of control how dense it can be.
So they're like putting limits on how tightly you can pack those connections in the hypergraph?
Exactly.
Okay, got it. And in this paper, they're looking at these degenerate hypergraphs where the maximum degree is bounded.
Right. So there's a limit on how many edges can connect to a single vertex.
Right, right. And they're specifically looking for the threshold where these things pop up in the Erdős Rényi model.
Exactly. That's the big question.
Which is like the classic way to make a random hypergraph, right?
It is, yeah.
You start with n vertices, and then you just flip a coin for every possible set of k vertices to see if you add an edge.
That's it. You got it.
And so they're trying to find that sweet spot as you increase the probability where suddenly, boom, you get these degenerate hypergraphs.
Exactly. At what point does it tip over from unlikely to likely?
Yeah, and they actually find a new upper bound for that threshold.
They do, which is a big deal.
Which is exciting.
Right, it is. It's a big step forward.
So it's in theorem 1.4, they show that the threshold is at most n to the -1 over d.
Right, and that tells us a lot about how these complex structures appear out of just randomness.
So this is all super interesting just from a math perspective, but I'm kind of curious too, like, what does this actually tell us about, the world around us? Like, what's the broader impact of this kind of research?
That's a great question. And it might surprise you how many different fields this kind of research can impact.
Okay.
Like, think about social networks, for example.
Right.
You can model them as graphs where people are vertices and connections are edges.
Okay, I see that.
And understanding these thresholds can help us understand things like how information spreads or how communities form.
Oh, wow. So it's like you could maybe predict trends or even design ways to spread information more effectively.
Exactly. Or even figure out how to combat misinformation.
Oh, that's interesting.
Yeah, it's really powerful stuff.
So it's not just about these abstract hypergraphs. It's about understanding how networks work in the real world.
Exactly how complexity arises from randomness.
Okay, so let's move on to the introduction where they lay out the background for their work.
Right.
They talk about this thing called the Kahn-Kalai conjecture, conjecture 1.1, which seems to have been kind of driving a lot of research in this area.
It has. It's been a major motivator.
Can you remind us what that conjecture is all about?
Basically, it says there's a connection between the expected number of copies of a graph you'd find in a random graph and the actual point where that graph starts to show up.
So it's trying to link the probability to the reality of seeing that structure?
Exactly, trying to bridge that gap.
And this paper is kind of pushing the boundaries of what we know about that relationship, especially for these degenerate hypergraphs.
Yeah, they're really making progress in that area.
Okay, cool. And they do this by introducing some new tools and concepts, especially this idea of spreadness.
Yeah, spreadness is key here.
But before we get into that, I think we should clarify some of the specific definitions they're using.
Good idea. Let's make sure we're all on the same page.
So they jump right into definition 1.2, which formally defines a degenerate K-uniform hypergraph.
Right. Let's break that down.
It's a bit dense. It says that a K-uniform hypergraph G is degenerate if it meets two conditions.
Okay, two conditions.
First, for every non-empty subset S of vertices in G, the ratio of the number of edges within S to the number of vertices in S is less than or equal to D.
Right, so that's putting a limit on how many edges can be packed into any subset of vertices.
Okay, so it can't be too dense anywhere.
Exactly.
And then the second condition is there exists a sequence of subsets of vertices S0, S1, and so on up to SL, where S0 is the empty set, and SL contains all the vertices of G.
Okay, a sequence of subsets.
And for each of those subsets, two things have to be true. The size of the difference between SI and SI1 has to be bounded by a function of I and N, the number of vertices in G.
Right, so it's controlling how much each subset can grow.
Okay.
And the second thing is that the number of edges that have at least one vertex in SI, but no vertex in SI1, is also bounded by a function of D, I, and N. So that's limiting how many edges can cross between these subsets.
Okay, so basically it's putting these really specific constraints on how the edges can be arranged within the hypergraph.
Exactly. It's all about controlling the density and the distribution of the edges.
To make this more concrete, they give us some helpful examples in example 1.3.
Oh yeah, the examples are good.
They point out that D-degenerate graphs are a special case of these D-degenerate hypergraphs.
Right, so we can see how this concept applies to things we're already familiar with.
Can you remind us what a D-degenerate graph is?
Sure, it's a graph where every subgraph has at least one vertex with degree, at most D.
So like no matter what part of the graph you look at, you can always find a vertex that's not too connected.
Exactly. It's all about limiting the local density.
And this idea extends naturally to hypergraphs then.
It does. And they give other examples too, like planar graphs, powers of cycles, and tight cycles, all of which are also degenerate.
So this property shows up in a lot of different places, not just simple regular graphs.
Yeah, it's a very versatile concept.
Okay, I think these examples are really helpful to kind of ground this abstract definition in something a little more tangible.
Definitely, they help make it more concrete.
Awesome. Well, let's dive into the main result of this paper, theorem 1.4.
Okay, the heart of the matter.
It says, let KU2, DU1, DU1, and 0 be given constants.
All right, setting up the parameters.
That for sufficiently large n, if G is an n-vertex, D, I wrote degenerate, K-uniform hypergraph, with maximum degree at most, B show, then P equals n to the negative 1 over D is an upper bound on the threshold function for G in G, K, and P.
Okay, deep breath.
That was a lot.
So basically what they're saying is if you have this degenerate K-uniform hypergraph G with a bounded maximum degree.
Okay, keeping track of all those conditions.
And you're generating a random hypergraph using the Erdős Rényi model with probability P.
Right. flipping those coins.
If P is greater than n to the -1 over D, then you're almost guaranteed to find a copy of G in that random hypergraph.
So it's giving us a concrete probability threshold.
Yeah, that's the magic number.
And it depends on D and N.
Exactly. Those are the key parameters.
I have to say, I really appreciate the elegance of this theorem. It's connecting these really abstract properties of the hypergraph to the behavior of this random model.
I agree. It's beautiful how it all comes together.
This has been a great start to our deep dive. We've covered the key definitions in the main theorem, but there's so much more to explore. So let's pick this up in part 2.
Looking forward to it.
All right, see you then.
See you then. Okay, so picking up where we left off, the authors really get into the details of their proof for theorem 1.4, and they bring in this really important idea of spreadness.
Yes, spreadness. I remember that word from the abstract. It seemed like a key part of their approach, and it sounds kind of intuitive, you know, like spreading something out evenly, but I bet it's a lot more subtle than that when we're talking about hypergraphs.
Yeah, you're right. It's not just about spreading things out physically. It's more about how evenly the embeddings of one graph into another are distributed.
Okay, embedding. So we're talking about like fitting one graph into another graph.
Exactly. Imagine you have a smaller graph G and you want to fit it into a larger graph H. And embedding is basically a way to map the vertices and edges of G into H without breaking any of the connections.
Okay, so it's like finding all the different ways you can fit a puzzle piece G into a bigger puzzle H.
Perfect analogy, and spreadness is all about how evenly those puzzle pieces are scattered throughout the bigger puzzle.
Okay, I can see why that would be important if they were all clumped together. It might mean that the structure is just appearing because of some local density, not because it's really a feature of the random process.
Precisely, spreadness helps us distinguish between structures that are just artifacts of local density and those that are more like a global phenomenon.
So it's about making sure that the structure is truly representative of the whole random graph.
Exactly. We want to make sure it's not just a fluke.
Now, they introduced 2 specific definitions of spreadness, Q-spread and Q-vertex spread. Can you walk us through those?
Sure. So definition 2.1 defines a probability measure on the edges of a hypergraph H as Q-spread if for any subset of edges S, the measure of S is at most Q times the size of S.
Okay, so it's putting a limit on how much probability any subset of edges can have.
Right, no subset gets too much of the pie.
And then definition 2.2 takes this idea and applies it to vertices instead of edges.
Right, it defines Q-vertex spread for a probability measure on the embeddings of G into H.
So instead of looking at how much probability goes to each subset of edges, it looks at how much probability goes to embeddings that use certain vertices.
Exactly, it's making sure that the embeddings are spread out across the vertices of H.
Okay, so it's like a fairness condition for both edges and vertices.
Yeah, exactly. Making sure everything is balanced.
To illustrate this, they give us fact 2.3, which says that the uniform distribution of embeddings in a complete uniform hypergraph is a vertex spread.
Right. That's a good example.
Can you remind us what a complete uniform hypergraph is and why this fact is important?
So a complete uniform hypergraph is like the most connected K-uniform hypergraph you can have. Every possible set of K vertices forms an edge.
Okay, super connected.
And this fact tells us that even in this extreme case, there's still a certain level of spreadness in how you can embed smaller graphs into it.
So it's like setting a baseline showing that even in the most connected scenario, there's a limit to how concentrated the embeddings can be.
Exactly. It's a really important observation.
Okay, then they introduce proposition 2.4, which seems to connect these spread distributions to the threshold function.
Right. It's a crucial link.
It says, let K2 and H2 be integers. Let G be an n-vertex K-uniform hypergraph with maximum degree at most each. Let H be an n-vertex K-uniform hypergraph if there exists a Cn-vertex CRED distribution on MBGH, then key Cn1 mil G is an upper bound on the threshold function for G in GK.
That's a mouthful. But basically what it's saying is, if you can find a certain kind of vertex spread distribution on the embeddings of G into H, then you get an upper bound on the probability threshold for G to appear in a random hypergraph.
That was like a shortcut. You don't have to do all this complicated probabilistic analysis if you can establish the right kind of spreadness.
Exactly. It simplifies things a lot.
And what's M1G?
That represents the maximum density of G. It measures how densely the edges are packed in any part of G.
So it's taking into account the structure of G itself to refine the threshold.
Exactly. The more densely connected G is, the lower the threshold needs to be for it to appear in a random hypergraph.
They mentioned that this proposition is related to a theorem from a previous paper by Frankston, Kahn, Narayan, and Park.
Oh, yeah, that's an important connection.
Can you tell us a bit more about that?
Sure. So that earlier paper also gives an upper bound on the threshold function, but they use a different approach. They focus on something called the fractional expectation threshold, which is a bit more technical.
Okay.
But Proposition 2.4 uses this idea of spreadness, which is more intuitive and maybe even more powerful in some cases.
So it's like they found a more elegant and maybe even more accessible way to get to a similar result.
Exactly. And that connection to earlier work really highlights how important their contribution is.
It's not just a new result, it's a new way of looking at things.
Right. A new perspective.
Okay, this is all super exciting. But before we go any further, I think it's worth taking a step back and asking, why are we so interested in these thresholds in the first place?
That's a great question, and it goes beyond just hypergraphs and random graphs. It's about understanding how complexity arises from randomness.
Okay, so it's like a fundamental question about how the universe works.
Exactly. These thresholds help us understand how likely it is for certain structures to appear just by chance versus being the result of some underlying design or process.
So it has implications for all sorts of fields, like social networks, biology, computer science.
All sorts of things.
So it's not just about the math, it's about understanding the nature of complexity itself.
Absolutely.
Okay, this deep dive has been so illuminating. So far, we've gone from abstract definitions to concrete examples, from technical propositions to these really broad implications.
Yeah, it's been a great journey.
And I can't wait to see where it takes us next. So let's continue this exploration in part 3.
Sounds good. Let's do it.
Okay, so we're back and ready to keep going with these degenerate hypergraphs and this idea of spreadness.
Back for more.
Now, you mentioned before that they introduced like an even stronger version of spreadness. They call it Spiro's spreadness.
Yeah, that's where things get really interesting.
This sounds kind of intimidating, but I'm curious to see how it builds on what we've already talked about.
It's definitely a step up in complexity, but it's needed if you want to get those really tight bounds thereafter.
Okay, so let's start with the definition. Definition 2.5.
Okay.
It says, let Q0 and R0 be integers.
All right, setting the stage.
Let H be an R0 bounded hypergraph.
Got it.
We say a probability measure on EH is QR0R. Spread if for every one array I and every set SERI.
Oh, okay.
We have ESEI. We have ECHO SESEI.
Deep breath.
Wow, that's a lot to unpack.
It is. It's a bit dense.
So we have this sequence of integers, the R's, and they're like defining different sizes of sets.
Right, different scales to look at.
And then for each of those sizes, it's putting a limit on the probability that an edge from H overlaps with a set of that size.
Yeah, it's controlling how much the edges can cluster around sets of different sizes.
Okay, so it's like a more refined control on the probability distribution.
Exactly, more fine-grained than just regular spreadness.
Okay, I'm starting to see the picture. So Spiro's spreadness is like making sure that no matter how you divide up the vertices, the probability of finding edges that overlap a lot is always kept under control.
Precisely, it's a much stronger condition.
And that's what lets them get those tighter bounds, right?
Exactly. It gives them more leverage.
Now, how does this Spiro spreadness actually come into play in their main result? They mention theorem 2.6 as like a stronger version of a key theorem in random graph theory.
Ah, yes. Theorem 2.6.
Which seems to connect this Spiro spreadness to the probability of finding edges within random subsets.
Right. It makes the connection between spreadness and subgraphs.
Can you tell us more about that?
Sure. So Theorem 2.6, which actually comes from Spiro's work, says that if you have a Spiro spread distribution on the edges of H, then the probability of finding a small hypergraph F as a subgraph of H is bounded by a certain function.
Okay, so it's using the spreadness to say something about subgraph.
Exactly. It's translating the spreadness into a probability statement.
And this connection between spreadness and subgraphs is what they use to prove Theorem 1.4, right?
It is. It's a key ingredient.
Okay, so let's move on to Theorem 2.7, which they call the core result of the paper.
Right, the heart of the matter.
It says, let can 2, Heyo 1, Do1, and 0 be given constants. Then there exists a constant C such that for sufficiently large n, if G is an n-vertex D degenerate K-uniform hypergraph with maximum degree at most, and H is an n-vertex K-uniform hypergraph, and if there exists a Cn-vertex spread distribution on MBG, then there exists a Cn1D R02 spread distribution on copies of G and H, where R0 or RRL are as defined in the proof.
Okay, so what they're saying here is that if you have a good vertex spread distribution on the embeddings of G into H, then you can create a spiro spread distribution on copies of G within H.
So it's like they're upgrading the spreadness.
Exactly. They're taking the vertex spread and using it to create something even stronger.
And why is that so important?
Remember, spiro spreadness gives us much tighter control over the probability of finding subgraphs.
Right.
So by constructing this spiro spread distribution, they can get a much better upper bound on the threshold function for G.
Okay, it's all coming together now.
It's all connected.
They use this superspreadness to prove that the threshold is bounded by n to the -1 over d, just like they said in theorem 1.4.
Exactly. It all fits.
I know we've skipped over some of the technical details of their proof, but I think it's important to appreciate how clever and how rigorous this kind of math research is.
It is. It's really impressive.
They're not just playing around with symbols. They're building a really careful argument, step by step, to prove something really deep.
That's like a work of art.
Okay, before we wrap up, I want to mention section 4 of the paper where they talk about an additional note.
Oh, yeah, the latest developments.
It seems like even as they were writing, this new research was coming out.
It's a fast-moving field.
They mentioned the work of Tom Kelly, who came up with an even more refined version of spreadness.
Yeah, he's taken it to the next level.
Which could lead to even tighter bounds, what they call a semi-sharp threshold.
Yeah. It's amazing how much progress is being made.
So it's like this paper is just one chapter in a much bigger story.
It is, and the story is still being written.
This has been such an incredible journey into this world of degenerate hypergraphs and spreadness and this whole idea of how randomness and structure are connected.
It's been a lot of fun.
We've seen how these really abstract math ideas can tell us something real about how complex systems work in the world.
It's the power of math.
So to our listeners, we leave you with this thought to think about.
Okay.
As we keep exploring these complex networks, what other things might we learn from these new ideas about spreadness?
Good question.
How will this change our understanding of things like social structures, or the spread of diseases, or even the universe itself?
So much to discover.
The possibilities are really endless, and the journey goes on and on. So keep exploring, keep asking questions, and keep being amazed by the power of math.
Couldn't have said it better myself.
Hey everyone, and welcome to another deep dive. Today we're going to be looking at degenerate hypergraphs.
Oh, very cool.
Yeah, it's going to be a fun one. And we're going to be basing this deep dive on a paper called On the Thresholds of Degenerate Hypergraphs.
Okay.
It's by Yu Chen, Jie Han, and Haoran Luo. And as always, you guys are all math experts, so we're going to jump right in.
Sounds good.
So the paper starts by discussing the Erdős Rényi random graph model. You know, like when you're trying to win the lottery and you're like connecting all the random numbers.
Yeah.
It's all about probability and how these structures emerge in these random formations.
Right. And so this model is sort of the foundation for understanding random graphs. And it's going to help us analyze what are called degenerate hypergraphs.
Okay, so those are what we're really focusing on today.
Exactly.
Could you explain exactly what a degenerate hypergraph is? I'm assuming it has something to do with the density of the edges.
Yeah, so you're on the right track. It's all about like a controlled density in the graph. Right. So formally, this means the maximum average degree, which is denoted as m sub 1 sub g, is less than or equal to d.
Okay, that makes sense. So E is like the limit for how connected the graph can be.
Yeah.
But what about the 8? What does that control?
Right, so that's where the local density control comes in. So for any subset of vertices in the hypergraph I is going to be helping to limit the number of edges within that subset.
Okay, so it keeps even zoomed in parts of the graph sparse.
Exactly. And the paper goes into a lot more detail about that.
Cool. Do you have any examples of degenerate hypergraphs that we might already be familiar with?
Yeah, so a really good example is a planar graph, which is one that you can draw on a flat surface without any edges crossing.
Okay.
And those fit the bill as 3 degenerate. And that's because of the rule that the number of edges in a planar graph is always less than or equal to 3 times the number of vertices minus 6.
Oh, that makes sense.
Yeah, another example is powers of cycles. So you take a cycle and then you connect every pair of vertices that are at most r steps apart.
Okay.
And then you get the rth power of that cycle. And those are r21 degenerate.
Gotcha.
So you can kind of imagine the cycle getting denser and denser as you increase RF.
Okay, I'm starting to picture it now. So now the paper talks about this idea of a threshold.
Right.
what exactly does a threshold mean in this context?
So imagine that we are slowly increasing the probability P of adding edges in this Erdős-Rényi model.
Okay.
At first, the chances of spotting a specific deduced degenerate hypergraph is really small, but as we crank up that P, something interesting happens at a specific point where the probability of finding our hypergraph suddenly skyrockets, and that tipping point is what we call the threshold.
So it's kind of like a point where things shift dramatically.
Exactly.
Below the threshold, it's not likely to show up, but above it, it's almost guaranteed.
Exactly.
Okay, cool.
Yeah.
And the paper mentions the Kahn and Kalai conjecture.
Right.
Does that relate to this idea of thresholds?
Absolutely. So it's a conjecture about the relationship between thresholds and the expected number of copies of a graph in this random model.
Okay.
And in simple terms, if you expect to see at least one copy of your graph on average, then the conjecture suggests that the actual probability of finding at least one copy should be pretty high.
Okay, so they're trying to understand how likely it is to find these degenerate hypergraphs within a random graph and using thresholds as a guide.
Exactly. And actually, the paper builds upon a previous work by Riordan, who established an upper bound for these thresholds.
So he set like a limit for how high these thresholds can be.
Right.
Cool.
But his work didn't always yield the tightest possible bounds, so this new research is trying to refine those bounds even more.
So it's diving deeper into how degeneracy affects these thresholds.
Exactly.
Is that where theorem 1.4 comes in?
So theorem 1.4 focuses on degenerate graphs that also have a bounded maximum in degree. And it states that the threshold for these graphs is less than or equal to unsup 1 die sup, where n is the number of vertices in the graph.
So how does that improve on Riordan's earlier findings?
So Riordan's work suggested a threshold bound of n sub 1 sub 2 sub g, right, where n sub 2 sub g measures the graph's density. But for degenerate graphs, m sub 2 sub g can sometimes be bigger than d.
Okay.
So Riordan's bound wasn't always the tightest.
So theorem 1.4 gives us a more accurate picture.
Precisely.
Awesome. Okay, that makes sense. Now, the paper also mentions locally sparse graphs.
Yeah.
How do those fit into all of this? Can you give us a quick explanation of what they are?
So imagine a landscape with a bunch of open spaces.
Okay.
That's kind of like a locally sparse graph.
Okay.
Even if you zoom in on any specific region, you won't find too many connections all bunched up together.
So even if the whole network is dense, there's still some space in local connections.
Yeah, that's a good way to put it. And formally, a locally sparse graph means that for any subset of vertices with size between d and a fraction of the total number of vertices, the edge boundary of that subset is at least d plus 1.
Edge boundary, what does that mean?
So the edge boundary of a subset is the set of edges that connect vertices inside the subset to vertices outside the subset.
Okay, so it's like the fence separating it from the rest of the graph.
Exactly. And so a large edge boundary means that there aren't too many connections within the subset itself.
Okay, cool. I get it. And there's a connection between locally sparse graphs and degenerate graphs, right?
Right. So a D regular graph that's D locally sparse also happens to be D to 12 degenerate.
Okay, so they're linked.
And the paper uses this to establish corollary 1.5, which states that the threshold for a sequence of D locally sparse D regular graphs is n sup to D sup.
Okay, I'm following. But then they construct this D regular graph that kind of breaks this rule.
Right.
It has a minimum edge boundary, meaning it's not locally sparse, but its threshold is a lot larger than n sup to D sup.
Right, and so that example is there to show that corollary 1.5 represents the best we can do in terms of D regular graphs.
Okay, so if we weaken the condition on the edge boundary, then we don't see the same behavior with the threshold.
Exactly.
Okay, cool. Now, another concept that this paper mentions is spreadness.
Yes.
Can you explain what spreadness is and why it's important for this research?
So spreadness is basically a way to measure how evenly a probability measure is distributed over the edges of a hypergraph.
Okay.
So imagine you have like a bag of marbles.
Okay.
And each marble represents an edge.
Got it.
And you want to distribute these marbles into different boxes.
Okay.
With each box representing a subset of vertices, and a Q-spread measure is like a rule that says no box can hold more than a certain fraction Q of the total marbles, no matter what subset of vertices you choose.
So it's like a fairness rule.
Yeah, like a fairness rule.
Awesome. And this idea of spreadness is really important for understanding thresholds. So if there's a probability measure on the copies of a graph within the complete graph that has good spreadness,
right,
then that graph has a high probability of appearing in the Erdős-Rényi random graph when the probability P crosses a certain threshold.
That's right.
Okay, so good spreadness means it's more likely our hypergraphs will show up.
Right.
Cool. And then they use vertex spreadness,
Right.
which was introduced by Pham, Sawney, and Simpkin.
So vertex spreadness is very similar to spreadness, but instead of looking at how edges are spread over subsets of vertices, it's looking at how the vertices themselves are mapped in embeddings.
Okay, so it's kind of like a zoomed-in version.
Right.
Okay, and they use this to set upper bounds for thresholds.
That's right.
Gotcha. And then they also talk about Spiro's spreadness, which is even stronger.
Right. Spiro's spreadness adds even another layer to this, and it's more specific.
Okay, so they're refining the tool to get a clearer picture.
Exactly. And this refined spreadness, together with theorem 2.6, helps to determine when a random subset of vertices is likely to contain an edge of our hypergraph.
Cool. Okay, so this is getting pretty complex.
It is, but it's really interesting stuff.
Yeah, it is. So now this all leads up to theorem 2.7.
Right.
Which connects vertex spread distributions and spread distribution on copies of the graph.
Exactly.
So it's linking two ways of measuring spreadness.
Right, and it's really powerful. Theorem 2.7 shows how degeneracy affects the relationship between vertex spread and the spread of copies of the graph.
Okay, that's a little abstract for me. Can you explain how this helps us understand thresholds?
Yeah, so theorem 2.7 allows us to get rid of a logarithmic factor that was in previous results on thresholds.
Okay, so it gives us a more accurate picture.
Exactly.
Awesome. And they go even further and refine theorem 2.7 using Kelly's work.
Yeah, they use Kelly's work to refine the theorem even more, and it shows just how much this area of research is always evolving.
This is super cool.
And we've only just scratched the surface. There's so much more to go into detail on, including the proofs of these theorems.
Okay, I'm ready when you are.
Let's do it. Welcome back to our deep dive on degenerate hypergraphs. So we just laid out all these key concepts, and now it's time to get into the math behind it all.
Okay, let's do it. Before we get into the proofs themselves, can we take a step back and just outline the overall strategy for proving these theorems? Like, what's the general approach?
Yeah, for sure. So basically, it all comes down to connecting vertex spreadness with the probability of finding certain subgraphs within a random selection of vertices.
Right, and we talked about vertex spreadness before and how it's all about how evenly a probability measure is distributed over the embeddings of a graph.
Exactly. And the other key concept here is the probability that if you choose a random subset of vertices, that it's going to contain an edge from a specific hypergraph.
Okay.
And so what the researchers do is show that if you have a probability distribution with good vertex spreadness, and that means there's a high probability of finding those edges we're looking for within random subsets.
Oh, so they're linking how vertices are mapped and the chances of finding certain edges in random selections.
Precisely, and this is going to be super helpful for proving those results about thresholds.
Awesome. So where do we start with these proofs?
So let's look at proposition 2.4, which basically bridges the gap between spread distributions and vertex spread distributions.
Okay.
And it states that if you have a CM vertex spread distribution on embeddings of a hypergraph G into another hypergraph H, then there also exists a C sub 2.4 sub 1 sub G spread distribution on copies of G and H.
Okay, that sounds familiar, but what does that actually tell us?
So basically it tells us that if there's good vertex spreadness, then that means there's also good spreadness on copies of the graph, which directly impacts the thresholds.
Okay.
And this implies that the threshold for G appearing in H is at most n sub 1 sub G sub times the logarithmic factor.
So it gives us an upper bound for the threshold based on that maximum average degree.
Exactly, but they didn't just stop there.
Of course not.
They wanted to get an even tighter bound by getting rid of that logarithmic factor. And that's where theorem 2.7 comes in.
Right, because theorem 2.7 is where we start talking about Spiro's spread its right.
Exactly. So theorem 2.7 basically states that if you have a CSON vertex spread distribution on embeddings of a DAS with degenerate hypergraph G into H, then you can find a C sub R sub 0 R sub spread distribution on copies of G in H.
Okay, wow. That's a lot. What are the key things we should be paying attention to there?
So let's start with that. D, degenerate hypergraph G.
Okay.
That condition is going to help control the density and make sure the hypergraph isn't too crowded with edges.
Gotcha. So we've got that well-behaved hypergraph.
Right. And then the seed sub 1 sub R sub 0 sub spread distribution is super important too. It's saying that we can find a probability distribution on the copies of G and H that satisfies Spiro's spreadness with some very specific parameters. So C, S sub, and sub, S sub 1 sub, and so on are going to be chosen very carefully to use the properties of DA degeneracy.
So those parameters are what make this work.
Right. They make sure that that spreadness measure is capturing the essence of the degenerate hypergraph.
Cool. Okay, and how does this help make that bound on the threshold tighter?
So the key here is that Spiro's spreadness with these special parameters lets us use theorem 2.6.
Right.
And theorem 2.6 links spreadness to the appearance of edges within those randomly chosen subsets.
Okay.
So if there's a probability distribution that meets this spreadness condition, then there's a really high chance that a randomly chosen subset of vertices is going to have an edge from our hypergraph G.
Oh, wow. So good vertex spreadness leads to good Spiro spreadness, which means a high probability of finding those edges.
Exactly. And then if we apply theorem 2.6 in this way, then we can get rid of that logarithmic factor from earlier.
So we get a tighter bound.
Right, a tighter bound of unsup 1d sup for the threshold.
That's really cool. It seems like they came up with all these tools just to figure out these hypergraphs and their thresholds.
It's really amazing, and that's not even all of it. Remember that they refined theorem 2.7 even more by using Kelly's work.
Oh, right. Kelly's work, which basically made Spiro's spreadness even stronger.
Exactly. It gives us an even more detailed way to look at the probability distribution, and that leads us to theorem 4.3.
Okay.
Which gives us a tight bound for the threshold and also creates what is called a semi-sharp threshold.
Semi-sharp threshold, what does that mean?
Think of it like a switch that flips really fast.
Okay.
So as we cross the threshold, the probability of finding our hypergraph jumps from almost 0 to almost 1 really quickly.
So below the threshold, we don't see it. And then as soon as we pass the threshold, it's almost guaranteed to be there.
Exactly.
That's pretty crazy. And this semi-sharp threshold is really important for understanding how these hypergraphs show up in random settings.
Right. It means the change happens really suddenly.
This is all so cool. It's amazing they can figure all this out so precisely.
It's a great example of how strong these mathematical tools they developed are. And this is only the beginning.
Yeah.
These findings could lead to all kinds of new research in areas like computer science and even physics.
Wow. That's awesome. It's crazy how these abstract concepts can affect so many other things.
It really is a great example of how fundamental research can lead to new and important discoveries.
This paper has given us so much to think about.
Yeah.
From all those details of degenerate hypergraphs to how important it is to understand thresholds. It's been an awesome deep dive.
It really has.
I'm ready to talk about what this all means.
Okay, let's do it.
All right, so we've gone really in depth on degenerate hypergraphs, learned about their thresholds, and even how the researchers proved all this stuff. But now I want to know, what does this all mean? Like, how does this abstract math connect to the real world? What are the potential applications for this research?
Well, that's the really fun part. It's not just about equations and theorems. It's about figuring out the rules of how structures come about from randomness. And that has implications that go way beyond just math.
So let's get into those implications. Where could we see this research having a real impact?
One area that comes to mind right away is network science. You know, networks are everywhere: social networks, biological networks, communication networks, the internet itself.
Yeah, for sure.
So knowing how structures form in these networks is really important for all sorts of things, like predicting how information spreads or building better systems.
That makes sense. If we can guess how certain patterns will show up in a network, then we can control it or make it better.
Exactly. This research could help us understand how groups form in social networks or how clusters of web pages pop up online. It could even help us understand how diseases spread.
Wow. So it's like having a special tool that lets us see the hidden structures in these systems.
Right.
What other areas could benefit from this?
Well, computer science could really use this research too, especially in things like making algorithms and machine learning.
How so?
A lot of algorithms depend on finding specific structures in graphs or networks, like algorithms that find the shortest path or spot communities.
Right.
They need to be able to recognize patterns.
So it's like finding a needle in a haystack.
Exactly. You have to know what the needle looks like and where it might be.
Yeah.
And this research gives us tools to figure out how likely it is to find those patterns, which can help us make better and faster algorithms.
So it's not enough to just find the patterns. We also need to know how likely they are to happen.
Exactly. And that knowledge is really powerful. For example, in machine learning, this research could help create algorithms that are better at seeing and sorting complex patterns in data.
That's really cool. It's awesome to see how this research connects the abstract math world with real-world problems in so many different areas.
It really is a great example of how basic research can lead to new and unexpected discoveries.
This paper has really given us a lot to think about.
I agree.
We've gone from the details of these degenerate hypergraphs to how important it is to understand thresholds. It's been a really cool deep dive.
It really has.
So, any final thoughts for our listeners today?
I would just say stay curious, keep asking questions, and keep exploring. You never know what amazing connections you might find.
Well said. And if any of you listening want to go even deeper into this world of math, we encourage you to check out the full paper by Jie Han and Liu Ban. Thanks for joining us on this deep dive. We'll see you next time.